All right, let's dive into one of the most critical and sometimes frustrating topics in all of networking, troubleshooting the spanning tree protocol. You know, STP is supposed to be our safety net, preventing those network-ending loops. But when it goes wrong, well, it can cause the very meltdowns it's designed to stop. So let's get into it. So let me just start with a question for you. When a big enterprise network goes down, and I mean really goes down, phones ringing off the hook, everyone's offline, what's one of the most common culprits that's usually hiding in the shadows? If you've ever been in the trenches, you already know this feeling all too well.
You got it. Spanning tree protocol. It's this double-edged sword, right? It saves us from layer 2 loops, but a single misconfiguration can bring everything to a screeching halt. So today, we're going to tackle some real-world STP failure scenarios, CCIE style. The goal? To go from just troubleshooting STP to truly mastering it.
Okay, first up, we have an absolute classic, the wrong route bridge. This is that fun situation where your network traffic decides to take the long, scenic route to its destination, and not in a good way. Performance tanks, and you can be sure the help desk tickets start piling up. The symptoms here are just painful. You've spent all this money designing a super fast, high-capacity core network, but suddenly, all your data is getting funneled through some little underpowered access switch in a closet somewhere. It's like trying to force all the traffic from a 6-lane highway down a residential side street. The result is just total network congestion. Everything feels slow, clunky, and just plain broken. So how do we prove our theory? Well, our first stop is always this command, show spanning tree VLAN 10. Think of this as our X-ray vision into the STP topology. We're hunting for one very specific line. This bridge is the route. If you see that message on the wrong switch, you found your smoking gun. And this slide just lays it out perfectly. On the left, that's what we wanted to happen. Our big, beefy core switch should be the root. We do that by giving it a really low, attractive priority number. But over on the right, that's reality. Some random access switch won the election. And why? Probably just because it happened to have a lower MAC address. The network is running on pure chance. So understanding the root cause is everything. The problem happened because the election was basically a coin toss based on MAC addresses. Nobody told the network who should be in charge. The fix is to stop leaving it to chance and take control. We get on our core switch, and we issue the command spanning tree VLAN 10 priority 4096. This low number basically shouts to the rest of the network, hey, I'm the boss now, and forces it to become the root, snapping our traffic paths back to where they should. And here is the absolute key takeaway, the real CCIE insight. You never, ever rely on a MAC address for your root election. That's just lazy network design. A stable, predictable network is one that you've designed intentionally. You have to tell Spanning Tree exactly who's in charge. All right, so now that we know how to put the right switch in charge, let's look at a different, super frustrating problem. You've got a link, it's physically up, all the lights are green, but it's not passing a single packet of data. This is a classic port forwarding failure. You know the drill. You check the interface, show IP interface brief, and it says up, up. Everything looks healthy. But when you dig a little deeper, you realize the port is stuck in a discarding or blocking state. It's like a ghost link. It's physically there, but Spanning Tree has logically shut it down. To hunt this ghost, we need a more powerful tool. The command we need is show spanning tree interface gig 0/1 detail. This is our magnifying glass. It doesn't just tell us that the port is blocked, it gives us the critical clues we need to figure out why it's blocked. And the detailed output gives us our list of usual suspects. Is the port just doing its job correctly? Maybe it's an alternate port, a backup path that's supposed to be blocking. Or has one of our safety features, like root guard or loop guard, been tripped? That would point to a much bigger problem somewhere else in the network. This brings us to a really crucial piece of expert advice. When you see a port is blocking, don't just immediately assume something's wrong. The first step is to figure out its role. Is it a root port, a designated port, an alternate port? Once you know its role, then you can start asking why Spanning Tree gave it that role. That systematic process is the fastest way to solve these kinds of problems. All right, let's talk about those special features that are designed to protect us, but can sometimes create their own brand of trouble if we're not careful. I'm talking about STP's protection mechanisms. First on the list is BPDU Guard. The symptom for this one is pretty dramatic. You go to plug a new device into a user's port and bam, the port light goes amber and the interface immediately shuts itself down, going into what's called an error-disabled state. It looks like the port just broke, but really it's doing exactly what it was told to do. So what's the real cause? It's a simple policy violation. You have a rule on that port that says, this port is for end-user devices only, like computers or phones. No switches allowed. The moment it sees a BPDU packet, which is spanning tree's hello message from another switch, it slams the door shut to prevent a potential loop. The fix is easy. Unplug the switch that doesn't belong there. And this is a really important mindset shift. BPDU guard isn't the problem here. It's the solution. It's a security feature that worked perfectly. The real problem is that the physical reality of what was plugged in didn't match the software policy configured on the port. The tool is working, it's just being used on the wrong connection. Okay, next up is Loop Guard. Now this one protects us from something way more sneaky and dangerous, a unidirectional link failure. You see this a lot with fiber optic cables, where maybe one strand of the fiber breaks, but the other one keeps working. This can create a silent but absolutely deadly network loop. The symptoms here are just pure chaos. Your network is completely drowning in a broadcast storm. The CPU on your switches is pegged at 100%, but when you look at your monitoring dashboard, every single link is green. It's maddening. What's happening is that BPDUs aren't being received on one side, so a backup port thinks the main path is gone, it opens up, and bam, you've got a massive loop. And here's a tip that could literally save your job someday. If your network is melting down in a broadcast storm, but every link looks perfectly healthy, your number one suspect has to be a unidirectional link failure. LoopGuard is the feature that prevents this chaos by putting the port into a blocking state if those BPDUs suddenly vanish. Okay, let's turn up the difficulty a bit. For our last scenario, we're jumping into the deep end with multiple spanning tree, or MST. Now, MST is an incredibly powerful tool for load balancing across your network, but it has one tiny requirement: absolute perfection in its configuration. And this table shows you just how unforgiving it is. Just look closely. Switch A and Switch B have the same region name, same revision number. Everything looks good, but then you see it. In instance 1, Switch B is missing VLAN 30. That tiny typo, that one little omission, is enough to completely break the MST region. These two switches will now see each other as being in different regions, and all that careful load balancing design goes right out the window. So what's the golden rule of MST? It's simple. Consistency is everything. It's non-negotiable. The region name, the revision number, and that VLAN to instance mapping table have to be identical, character for character, on every single switch in that region. Even one tiny mistake breaks the whole thing. So we've walked through a few pretty different failure scenarios, right? The wrong route, a blocked port, protection features, MST mismatches. But what's the common thread here? It's not about memorizing 100 different commands. It's about having a systematic approach. It's about having the CCIE troubleshooting mindset. And here it is. We can boil it all down to a simple 4-step method you can use every single time. 1. Always start at the top. Is the root bridge correct? 2. Trace the paths from there. What are the port roles and states? Are they what you expect? 3. Check your safety nets. Are protection mechanisms like BPDU guard or loop guard getting in the way for a good reason? And finally, the most important step of all. Don't just slap a Band-Aid on the symptom. Find and fix the underlying design flaw that caused the problem in the first place. And that really leaves us with the most important question you can ask yourself after you've fixed an issue. Yeah, sure, the immediate problem is gone. The network is back up. But did you actually solve the problem? Or did you just fix the symptom? Rebooting a switch is easy. Flapping a port is a temporary fix. But understanding why it broke and fixing the core design issue, well, that's what separates a network administrator from a true network engineer.